This time we'll be looking at very important concepts in circular motion, which is vertical circular motion. One will be asking, what is vertical circular motion again? We want to make it very clear that what we have discussed before is circular motion on the general notes, the most general case. But now I want to let you know that we have vertical circular motion and also horizontal circular motion. But let's refresh our memory. Generally, we say that circular motion takes place on the circular path through an axis. Assuming this is the point, this is the radius, and these objects move from this point to this point. Maybe this point A, point B, it makes an angle theta, and this is the distance on the path, on the circular path. We're able to define or explain what is angular displacement as S all over R. We're able to also define what is angular velocity as theta all over t. Angular acceleration as the omega t. We're able to also define what is centripetal acceleration as v squared all over r. And centripetal force as mv squared all over r. We also said that centripetal force can also be written as m omega squared r. Remember, from Newton's second law of motion, F is equal to ma. If this is the centripetal acceleration, we have defined the centripetal acceleration as a equal to v squared all over r. So by the time you substitute that, we have F equal to mv squared all over r. That's why we have this. So we also stated the relationship between linear velocity and angular velocity as v is equal to omega r. So by the time you take this component and substitute here, we have F equal to m omega r square all over this. So remember, this is r, this is one of them will go here, and F is equal to m omega square r, which is this. But that is not what we are discussing today. We just refreshed our memory. We are discussing vertical circular motion. What do we mean by vertical circular motion? Assuming you have an object like this, it has weight, and by the time you tie this to a string, inextensible string, and wheel it, it is performing vertical circular motion. Something like this. So, if you have this, two things are involved. This is the particle or the body that has a weight that is acting vertically downward. And then the tension on the, assuming this is the point A, the tension on the string called TA is acting in the opposite direction. So the sum of forces here is TA minus mg, which must be equal to the centripetal force. The sum of forces here is TA minus mg. They are acting in the opposite direction. That's the reason why we have this. Is that right? So in this case, if you want to make TA the subject, TA becomes mv square all over r plus mg, and this is our equation 1. What if this object turns and it's at the top here? Remember, at this point, the weight is acting vertically downward, which is mg, and the tension in this case, maybe this point B, the tension is Tb, and it's also acting in the same direction. So the sum of forces at the top here will be Tb plus mg, plus, because they are acting the same direction, equal to the centripetal force. So in this case, Tb will be equal to mv square all over r minus mg, and this will be our equation 2. Let's look at equation 1 and 2 very well. If this object is moving and it's at the top, it requires a minimum speed for it to maintain that circular motion. If that minimum speed is not acquired, the object can no longer maintain circular motion. And that speed is what we call v is equal to the square root of gr. That is what I want us to look at. How come about the v equal to square root of gr? Now, let's look at this. We have the net force equal to mv square all over r. Maybe this is equation 3. And the weight of the objects in question is equal to force equal to mg. And this is called equation 4. So by the time you look at equation 3 and 4, by the time you equate them, we'll have mg is equal to mv square all over r. On the left hand side, we have m. On the right hand side, we have m. So we can say that v square is equal to gr, and v will be equal to the square root of gr. Maybe this is equation 5. This equation 5 is the minimum speed that must be acquired by that object at the top to keep it in circular motion. So we want to look at, we have looked at a situation whereby the object is at this point, point A, point B. What if this object is inclined, is found here at point C? What happens? In this case, the weight is acting this way. And if you want to resolve this, we now have mg cos theta. We have done this several times. If you are resolving on the horizontal component, is cos theta. If you are resolving on the vertical component, sin theta. We have explained this severally. So in this case, the sum of forces here in this case will be the tension. Since they are moving in the opposite direction, minus mg cos theta is equal to mv square all over r. So tension now will be equal to the tension at C will be mv square all over r plus mg cos theta. And maybe this will be our equation 6. So if angle is involved, the object can be anywhere. Remember, we have looked at the point where it is down, where it's at the top, anywhere angle is involved, we can look at it. So we have a problem that we want to look at. A bucket of mass 8 kg is filled with water and is attached to a string of length 0.5 meters. What minimum speed must the bucket have at the top so that no water spills off at the top? So let's look at the solution. The formula is V is equal to GR. Take G to be 10 meters per second square. And in this case, R is 0.5 meters. So we can say that the speed will be square root of GR, which is equal to 10 times 0.5 square root, which is equal to 10 times half. Remember, 0.5 is half. So we now have square root of 5, which is 2.24 meters per second.